Good morning, everyone. Thank you so much for waking up so early and being here. I have to tell you, well, just what we discussed here. I'm a bit afraid because this is such a big room, such a great audience, and I have not a single line of C++ on these slides. Maybe you are happy for that. Not sure. I don't have benchmarks either, so we'll see what what we get here. We are going to talk about whether clean code implies horrible performance. But before we are getting into the details, let me quickly introduce myself. My name is Sandor Dargo. I work for Spotify. And yes, we do use C++ in Spotify. I've seen that it surprised a lot of people, but we have quite some code. In my free time, I like reading and writing. I write a lot about, not only, but mostly about C++ on my blog. But the fun fact is that during the last few years, I learned more and more about French wine and winemaking. And I started to write for some Hungarian online magazines about French wine. But I guess there's a language barrier there. And big thanks for my wife for taking care of the kids while I'm being here with you. I can enjoy this great conference. But that's more than enough about myself. Let's discuss a little bit about why I wanted to talk about clean code and performance. So in 2023, I gave a talk at C++ on C with the title, Why Clean Code is Not the Norm, or Why Clean Code is Still Not the Norm. And it led to some interesting follow-up discussions, both after the talk or in emails. And it gave me some ideas to talk about here. And, well, it was not a new realization there, but, well, it's quite general in life that many people, they like to talk in absolutes. For some people, things are either black or white. But I don't really like that approach, especially not in engineering. I think engineering is much more nuanced than that we can say that, OK, this is good, this is wrong. It's more complex. So we are going to talk about these complexities in the next hour. So let's have a quick look at the agenda. First, we'll try to define quickly what is clean code. Then we'll see what is software quality. Well, we'll try to see. Then we'll make a little detour to C++, and we'll discuss why do we use C++ at all, and where do we use C++. Once we are done with that, we are going to talk about performance, and we'll ask ourselves the question if clean code is actually slower. And if it is slower, then should we drop it for better performance? Well, maybe we'll get some answers, maybe we won't, but at least at the end, we'll ask ourselves the initial question again, does clean code imply horrible performance? Is it OK for you? Yeah? OK, let's get started. So first, what is clean code? Would you be able to define it in one sentence? Readability has big importance there, yeah? Well, sorry? Not dirty one, OK. So, OK, you start from what is not clean code. You say it's not dirty. And I came with the same approach. First, let's see what is not clean code. And clean code, to me, is not a closed set of rules. Speaking of which, I really appreciated the book Clean Code. I think it's a great book. But it's not the same as the concept of clean code. And that's why I use clean code in lowercase, because I'm not talking here about the book. I'm not referring to the book. So it's not a closed set of rules. And it highly depends on the language. If you write code that is considered clean, I don't know, in Java or Python, for example, and if you use the same approach in C++, most probably your code reviewers will not consider it clean code. So it depends on the language, but it also depends, or it might depend on the context. So for example, what is considered in, I don't know, in one industry like high-frequency trading, maybe it's not considered clean in the automotive industry. You use different standards, you have different expectations of clean code. And it also changes over time. If you remember what Peter Milden said on this stage yesterday, he said that in programming, paradigms change over time. So what you find acceptable changes. So what you find clean, it also changes over the time. What we considered clean in the 90s, probably we are not so happy with it nowadays. So that's why we cannot say that clean code is a set of closed set of rules. And it's definitely not a silver bullet that will solve all of your problems. It won't. Okay, so this is not clean code, but what is clean code then? I spent a lot of time trying to find a simple answer. As simple as possible, but not more simple than possible. And this is the phrase that I found the best. Clean code is code that is easy to understand, and at the same time, it's easy to change. But this is still, okay, it's just one sentence, but it's quite vague. So let's try to break this down. What does it mean, code that is easy to understand? Well, if it's easy to understand, then it should be easy to understand the execution flow of your application, of your code. Also, the different relationships between the objects should be easy to understand. But we should be able to go a bit deeper, and it should be easy to understand the roles and responsibilities of each object. And we should be able to go even deeper and understand easily the purpose of each expression. So yeah, that's pretty much about readability. But there is more to clean code, because we said that it should be easy to change. But when code is easy to change? Well, first of all, classes should have a concise public interface. They shouldn't be complicated. And they should be easily testable, but it's not enough that your code is easily testable. It doesn't make it easy to change. It should also be tested, because that's the only way to make it easy to change. And it should be predictable. If it works differently every single time you invoke it, then how do you know if it works correctly? And well, these different entities that we talked about, they should be small and with one single responsibility. So this is the definition of clean code that we are going to take with us. And I tell you that I think clean code is part of software quality. And I'll tell you why. But first, is high-quality software even important? Who is there who thinks that it's not important? Nobody. Well, I love this crowd. So all of you think, please hands up, is high-quality software important? Okay. I'd be happy to work with you. But quality is probably not so important all the time. So for example, when you build a proof of concept, or when you are still searching a product market fit, or you must deliver quickly in order to survive and to be faster than your competition, maybe you can sacrifice a bit of quality then. But otherwise, if you plan for a longer term, then yes, I also put my hands up, yeah, high-quality software is important. But, you say high-quality software is important. Could you define quality? Can you define software quality? Or quality in general? What does quality mean? Anyone? Okay. Maintainability. Does what it says. Yes?
Software that delivers on the market. It adds a business value. It actually adds something.
It adds a business value. Okay, yeah, that's also important. I think all of these answers are right, yet they are quite different. So if we try to define software quality, maybe we can try to define quality in general. But it turns out that this is not so simple. There were people, philosophers, spending their whole life trying to define quality, and they wrote several books just on trying to define this simple term. Yet it was not that easy. It turns out that quality is pretty much undefinable in itself. And at the same time, when you see something high quality, you recognize it. Now, at this point, I could make some jokes. I can tell some anecdotes about an American justice, but I was told maybe I shouldn't do that. So we are in Germany. Let's talk about German cars. It's difficult to define what quality is, but when you sit in a German car, you just feel it. Okay, this is comfortable, this is reliable, this drives well. You can't define it, but you feel it. You feel it. But that's not good enough for us, engineers, software engineers, if we want to talk about quality. So we have to dig deeper. And we are going to talk about software quality a bit, which has several definitions. If you check on Wikipedia, for example, you will find tons of definitions. And some will talk about the value the software provides for the business, for the users. Some will talk about maintainability. Some will talk about how it changes the world. There are way too many definitions. It means a different thing for almost everyone. And based on that, it might even be a meaningless term. So, for example, what the author of The Era of Software Quality, Derek Jones, wrote is that people in industry are very interested in software quality, and sometimes they have the confusing experience of talking to me about it. My first response on being asked about software quality is to ask what the questionnaire means by software quality. After letting them fumble around for 10 seconds or so, trying to articulate an answer, I offer several possibilities, which they are often not happy with. Then I explain how software quality is a meaningless marketing term. This leaves them confused and unhappy. People have a yearning for software quality, which makes them easy prey for snake oil salesmen. So people who are much better qualified to speak about quality, they also think that it's almost impossible to say what software quality is. So whatever I will say here, whatever definition I will use, well, take it with a pinch of salt. That's one way to see it. You might see it in a different way. But the one I picked is the definition of the CSIQ, Consortium for Information and Software Quality. They use 4 pillars. They use 4 pillars to define structural quality. One is security, something we talk a lot about these days. Another one is reliability, maintainability, and performance efficiency. Now let's see how this works with clean code. Because I said that clean code is part of software quality, but why? Well, it helps reducing the number of bugs. So if you have less bugs, probably you have a more secure software. It's definitely more reliable, and it helps with the maintainability as well. So we are good on those. But clean code also helps reducing the time to fix bugs. You remember, it's easy to understand and easy to change. And when you fix bugs, you have to change. So it helps. Then it helps with reliability and maintainability. And it definitely decreases the maintenance costs in the long term. So it improves the maintainability of your software. So let's get back to this definition. We are good with security, clean code helps. We are good with reliability, clean code helps. And maintainability as well. But we didn't say a single word about performance efficiency. What about performance? At this point, let's leave clean code and performance a bit behind us, and let's talk about C++. We just mentioned performance. Probably this is the right moment. Where do we use C++? Well, we use it everywhere. It's in your mobiles, it's in household appliances, cars, aviation, in photo editing software, 3D or not so 3D games, browsers, compilers, corporate software, trading, and in our favorite music app, in Spotify as well. C++ is just everywhere. But why? Why do we still use C++? Or why do we use C++? Shouldn't have said still. Well, it's legacy, right? Well, that's an answer. It's been with us since the 80s, right? It's a long time. And we have tons of existing code. I think it was Titus who said that we have something like 50 billion lines of C++ code. And it's often complex code and critical. Business critical, but maybe even life critical. And rewrites, they don't really make sense. Even if C++ is not needed for an application. I guess most of us have seen corporate code where it doesn't really matter which language you would use. Well, probably not a few languages. I don't want to mock any, but you could choose at least from a dozen of languages. It's just a tool. But the thing is, we still don't want to rewrite those because it would be a loss of time. Rewrites are rarely successful, but it's not simply a loss of time. It's a problem of existing ecosystem because, well, we all know that C++ doesn't have standard compiler, standard package manager, whatever. So probably your company is heavily invested on finding the best solution for those. And maybe you wrote your own tools, and you'd lose these as well. And you would lose a lot of knowledge. Because I'm not talking about C++ knowledge, but many of us, we don't want to work with other languages. Well, maybe we'll try Rust, maybe we'll try this or that, but probably we want to keep working with C++. And if our companies decide to move away, we also decide to move away. And we don't only bring the C++ knowledge with us, we also take the business knowledge with us, which is often not documented. So, yeah, it's in a certain way, C++ is legacy and it will stay, but C++ is more than that. It's evolving, because since C++ 11, we have a stable and steady evolution with a cadence of 3 years that Herb just explained yesterday. And we get safer and more expressive code regularly. So C++ is evolving. That's great. That's another reason to keep using the language. And it's not owned by a single corporation, like quite a few languages nowadays, which is probably better for us. And C++ also has an economic advantage. Have you seen this chart? Is there anyone who already saw this chart? Sorry? Yeah. You have power consumption, you have energy, time and memory consumption. And C++ has a clear economic advantage. Well, you see that C++ is not an outstanding language on its own. There are other highly performant languages as well, like C, Rust, Ada. But these languages have a clear advantage over some other languages when it comes to different types of consumption. So C++, what we can see, is fast. And it's good for performance-critical applications. It doesn't use a lot of space compared to other languages. So even if you consider the binary size, even if you consider the memory consumption, it doesn't use a lot, and it's good for the embedded world. Or actually, that's good for anything that has to be distributed, if you think about binary size. And it consumes less energy. And I guess apart from some energy companies, it's good for everyone. So if I want to summarize this with a small sentence, I can say that C++ is performant. And that's also a great reason to use it, especially when you combine it with the evolution and the safer and more expressive code every 3 years. But again, first we discussed about clean code. We didn't know what it is. We took a definition. Then we went to quality, but we had to define it. And now we have to talk about performance, software performance. But again, we have to define what performance means, because we use words, but often we don't really think about their meaning. And performance is, well, what is it? What do you think? How would you define performance? Could you define performance? Please.
Computations per watt?
Computations per what? Okay, that's a very engineering definition, yeah. Depends on the perspective. Yes, yes. I think both of you are correct. Well, when it comes to performance, I think that it's not just a non-functional characteristic of software, it's also a non-functional requirement. And these requirements, they depend case by case. Because different kinds of software will have different kinds of performance requirements. You can also say that it's a metric of efficiency, and then maybe you could say that it's the number of instructions per kilowatt. I think we will get back to something similar at the end of the talk. We'll discuss that as well. But what we discussed here is a non-functional requirement. Well, it's like quality. It's nothing really specific as a term. Because you can use some metrics like the one we mentioned, but maybe it doesn't really make sense in every case to go to such a deep level. And we'll see that there are different metrics. So let's just say that sufficient performance ensures that the software can achieve its functional requirements in a reasonable time span. And this means that what is a performance software in one context, the speed of that software might not be enough in a different context. So performance really, the meaning of performance means on its context. It changes case by case. But it has different aspects, because that's just one way to say that, well, we should be able to to execute a lot of instructions with a given unit of energy, but probably that's something difficult to measure in everyday situation. But at the end of the day, maybe that's what counts. But well, you can measure different aspects. You can measure how fast your software responds. Maybe you can check how many requests it can handle at the same time, or how efficiently it uses its resources. Depends what really matters to you for a given piece of application. Maybe you care more about the scalability of your software, or maybe it's the capacity that matters to you before your software starts degrading, how many users you can serve, or maybe even that is not so important to you, or you try to measure something else. Maybe you care more about the scalability of your software, and probably this will also depend on the type of software that you write. I discussed with some people here who are working on medical software. Probably for them, well, we already discussed reliability, but from these aspects, probably it's stability that matters them the most, and maybe scalability is less important, because probably you won't operate on several people at the same time with the same hardware, hopefully. But when you discuss in the hallway with C++ engineers or with C engineers, they talk about not really these different aspects. They just say, well, I want a great runtime performance. I do optimization because I want better runtime performance. And we didn't use the term. So what is runtime performance? When we define runtime performance, could you define runtime performance? Mm-hmm. Mm-hmm. Yes, yes. That's the thing. That's the thing, that providing absolute measures is really difficult when it comes to performance, or when it comes to quality, when it comes to clean code. It really depends case by case. You just want something fast. And is runtime performance maybe the same as execution speed? It's mostly, but not entirely. It's runtime performance won't be only about algorithmic complexity per se. It might be important, might be, not all the time, but the language is also important, what you use, maybe the compiler. The layers of abstractions can matter a lot, even if your algorithmic complexity is quite good, but you use a lot of different layers of abstractions, and maybe your runtime performance will suffer. It's a complicated question, and it's difficult, if not impossible, to provide just a single way of measuring it. But we know that if we neglect runtime performance, then probably other aspects that we saw will also suffer. But so we saw some aspects. Now we saw runtime performance. What other kind of performances are there that we might care about? Development performance. I didn't see who said it, sorry. Yeah, what does it mean? How fast you can deliver. Okay. Is it software performance? Well, you might argue that it is. How fast you can deliver? Well, we can also talk about like load performance. how fast our application loads in the beginning, and then we don't care maybe about the rest, but the startup is important. Maybe you want to optimize for scalability, efficiency, for startup time. There are a lot of different aspects. And if you say that, well, you prefer, let's say you prefer performance over clean code, you have to be able to say what kind of performance are you looking for. And maybe it's useless to chase certain kind of performance for certain kinds of software. But where am I getting with all these? Because we are just trying to define terms. We are getting deeper in this rabbit hole, but we lost clean code somewhere. So, is clean code actually slower? Well, clean code is actually slower than what? That's where I'm getting at. Maybe it's slower, but we have to be able to compare. Who recognizes this person? Leibniz, yeah. What did he say? Many things. He said many things. Probably one of the most well-known is that he said that, well, he believed that we live in the best world of all possible worlds. I don't know if he was right, maybe not, but I know something about clean code. Clean code is not the fastest of all possible codes. So when it comes to criticism of clean code from a performance perspective, obviously they are right in a certain way. Clean code is not the fastest code. Clean code is optimized code. But you can optimize for many things. Often when we talk about optimization, we talk about optimization for runtime performance, but we can optimize for different things. And clean code is an optimization for maintainability. So it's not going to be the most efficient or fastest code, and it's not going to be the smallest code either. If you care about binary size, for example, we do care a lot about binary size in Spotify. That's why I keep mentioning it. But the question is not really if it's the fastest code. The question is, will it hurt performance? Will it hurt your ability to ensure that your software executes with a reasonable performance, in a reasonable time span? Well, optimization is all about compromises, right? If you think about optimizing for runtime performance, what does it give to you? What does it come with? One thing is high speed, hopefully. The other is that it will hurt the readability of your code. And it might even hurt portability, depending on how you optimize, and it might hurt the binary size. Well, speaking of which, if you optimize for binary size, it can tell you that it will hurt readability, and it might hurt portability as well. And it will definitely hurt runtime performance. Mm-hmm. So I have a hard time.
Processor cache, if
Mm-hmm.
the algorithm fits into the cache, it might be much faster than if the algorithm might be, let's say, optimized, but no longer fit in the processor cache.
Okay, I see your point. Well, I talk in. I try to generalize here a little bit. Yes, there will be cases when you might end up in the sweet spot and you will have faster and smaller code. But in general, when you have hundreds of thousands of lines of code, and you try to gain a few megabytes maybe here and there, you will end up using some techniques that won't be so great. Not all of them, but many of them. At least that's my experience with it. I tried, sometimes I said, oh, okay, what's this? What is this here? Let's make it more readable. This doesn't make sense. And someone came that, well, we did that because we optimized for smaller binary, but we just didn't document it. So, and then, okay, I cancel my pull request. But when you optimize for readability, in most cases, well, not most cases, but often you will hurt runtime performance, especially if you compare it with code that was optimized for runtime performance. And you might hurt binary size as well with readability. I don't want to go into details of my examples for that right now, but if you want to discuss after, I'll be here. So then should we drop clean code for faster code? Because we see, okay, it's not the fastest possible code. Well, sometimes every bit of performance matters. So I collected here a couple of interesting drops of information. Maybe they are not up to date, but they give you the idea. Somewhere I read that every 100 milliseconds of latency costs Amazon 1% drop in sales. That's a lot of money. A broker could lose 4 million per microsecond in revenue. It's incredible. If a competitor is 5 milliseconds ahead, that's serious money. An extra 500 milliseconds in search page generation time dropped Google traffic by 20%. And how come I found that every 100 millisecond delay in a website load drops the conversion rate by 7%. In these cases, you might want to drop clean code, at least in some parts of the software, for the most optimized performance possible. Because we talk about a lot of money. But it's not always the case. And for example, performance for us in Spotify is also crucial, but maybe not the most important aspect all the time. But when you, for example, open the application, we want it to be as fast as possible. When you start playing a track, we want you to be able to enjoy the music or other types of content instantly. And basically, if you tap on any button, you should get an immediate feedback. But beyond that, there are more important aspects, at least for us, is small binary, because well, the application has to be distributed also in markets, in environments where you don't have virtually unlimited bandwidth, or phones maybe don't have such a big memory or storage. So it's important for us, and maintainable code as well, because, well, I know that many of us like to think that, well, for example, Spotify is a cool startup. No, it's not. It's a cool corporation with 10,000 people, and you know, people come and go on projects, and you have to ramp up yourself quickly to start to be able to contribute to another part of the code base, and it's not possible if it's not readable, and we have to fix bugs like all of us, and their maintainable code is more important than code optimized for runtime performance per se. But even when performance matters, when runtime performance matters, the first answer is not low-level code optimization. Or someone would even say premature optimization. That's not the answer. Because now I'm going to share a couple of stories. This is probably an embarrassing one from the beginning of my career as a software developer when, it was a horrible project, mismanaged as well, and I started to contribute to a project basically without any relevant C++ knowledge. And a few months later, we had the code review stage. And obviously, it was too late to make serious changes. But at the end, we shipped something. And it was slow. And it had a huge memory leak. Well, what was worse? What was the bigger problem? What do you think, speed or operability? You say operability. Well, interestingly, nobody said speed. I agreed with you. I thought that operability was a bigger problem because, before I was in operations, I was a database administrator before I decided to go into development. But there was someone else who said that, speed is a bigger problem. And he said that, you wrote here an algorithm that was quite complex. Imagine a for loop in a for loop in a for loop in a for loop. Yeah, it was that bad. But I wasn't really bothered by that code. I know that it gave the necessary results. I didn't know how to write it better. I know that it shouldn't be a problem, but I didn't really know how to measure code or performance. So what did I do? I opened the logs, I opened the notepad, and I started to collect data, and I calculated, and I realized that it was not a problem. That was not a problem. It only took a fraction of the execution time. Yes, it was horrible code, not the clean code that we talk about here, but it was really slow. But it didn't matter, because there's this gentleman here, Amdahl, and what did he say? Well, he said that the overall performance improvement gained by optimizing a single part of a system is limited by the fraction of time that the improved part is actually used. And that's what we know as Amdahl's law. So if you consider that piece of horrible code didn't matter at all because it was barely used. You can ignore slow code if it's not on the hot path. Probably code that you don't like because it's not performant enough shouldn't be your concern. In our case, the key was how we use the third-party library properly. I'm hesitating between I and we because we are not alone, but let's say it was me. And I called startup functions and cleanup functions more often than I should have. Documentation was not probably the greatest. It was definitely difficult for us to access it. For a lot of time, we didn't even know that we had it. But once we called them at the right time, it solved all the issues. We called startup and cleanup too often, and we had memory leaks. And it was also too slow. So guess what? Big surprise. Reading documentation and using libraries as they are intended to use is more important than writing fast code. Well, yes. Now, we jumped 10 years, and we were in a situation where we had to support 15 times traffic growth. So without giving exact numbers, because I don't remember them, I think we went from a few hundred transactions per second to a few thousand transactions per second. That's what we had to support. And actually, we didn't optimize our code at all. Well, if you consider those kind of performance optimization, we did something else. We had to make our system more scalable. We had to improve operability, resource utilization, and a few of us, well, it was definitely not me, spent a lot of time on fine-tuning network settings so that we could accept so many transactions. So what do I mean by improving operability? We had to remove memory leaks. We had to fix core dumps. We had to remove as much undefined behavior as possible. Apparently, it's going to be much easier than it was. And more importantly, we had to consolidate external requests. So you could optimize algorithms that are not optimal, but before you do so, consider your external requests, like network or database calls. They are orders of magnitudes slower than how you deal with your data structures, for example. If, for example, you have an API for some other systems for the database that offers some batching, use it. You might think that this is evident, but recently we saw some code that was very far from being readable and clean because the author tried to spare string allocation because he thought that it wouldn't be so great for the performance. At the same time, a network call was initiated in a for loop. Instead of using one batched call that we had the API for, we did it 100 times. But we spent time on sparing some string allocations. So I think these things are more important here. So if it's not possible, if you don't have that API, well, maybe you should build that API. You don't always have the option, but maybe you can try to batch it on call side, or you can try to use some caches. Locally, it will help you. It will help you way more than going to low-level code optimizations. Just try to think about anything that can help you reducing the number of these calls you have to make. It will do miracles. And now we discussed string allocation. So what about all those costly language features, that not all of, but so many of us just, hate? Will these common enemies ruin our performance? Like unnecessary heap allocations, copying large objects unnecessarily, or using virtual functions unnecessarily. Will they ruin your code, your performance? Well, or can you use them, actually, in clean code? So you might know this one, that the only valid measurement of code quality is I'm not supposed to say per minute. So you have, for good code, for clean code, you will not have a lot of those. But for bad code, well, there will be a lot of cursing behind the doors, or nowadays behind, I don't know, Zoom. So I think that, what I said about clean code, it depends on your language. And if your code is clean, if you aspire for clean code, you will not have many of these unnecessary allocations, whatnot, in your code. But you will have some. And it's okay. Some usage will not ruin your code. You don't have to optimize for all these things all the time. Optimization efforts must be concentrated, because as we saw from Amdahl's law, the overall performance gain is limited on a single part, and you should keep that in mind. And if you follow just the general best practices, general clean code practices of your language, you will end up with a reasonable performance. And if your performance is not good enough, just start optimizing the hot path. And you leave the rest clean as long as you can, as long as you prove that you should optimize that as well. Because performance, you don't optimize for performance for the sake of performance. You don't do that. What do you see on this image? There's a tire. There's a small piece of stone there stuck somewhere in the tire, and you try to remove it, while maybe the whole truck is crashed, and it won't go anywhere. It doesn't matter if the tire is not in the best shape. But I see something else there. That's many of us, developers, in a code review. We will say that, okay, I see that there is an unnecessary allocation there, but at the same time, there are much bigger architectural issues with the code, but obviously that's much more difficult to see. So you will try to, we will try to focus on what we can, but it's often the wrong way to see it. These things just don't matter all the time, because we tend to forget that software engineering is not, even in C or C++, is not about performance. Engineering is rather in the crossroads of defining what's good enough and recognizing when we reached that point. And just because we can do something, it doesn't mean that we have to do we have to do that thing. Just because we can make code faster, it doesn't mean that we should make the code faster. We have to be able to stop at a certain point, because we don't do competitive programming in our jobs. Well, maybe some of you do. I don't. So I think readability is more important. But why? Why is it so important? So I said in the beginning that we might get back to the point where we start discussing the number of instructions we can execute with a given unit with 1 kilowatt hour or something. Well, we are almost there. We are checking the cost per CPU clock cycle, and we can see that since the 70s, it's going down fast. And as you can see, that's a logarithmic scale there. So that's a big change. At the same time, software engineering salaries are going up. Maybe sadly not on a logarithmic scale, but we can't deny that in the software engineering industry, we can have quite good salaries. And if we put these two together, what we see is that we have cheap and strong hardware, cheaper and cheaper and stronger hardware, while developers are expensive. And usually we don't have enough of developers. And that's why I think, unless you prove else, you should optimize for readability, because developers as a resource are more scarce than hardware as a resource. That's the baseline. You might be in an industry, you might be in a company where it's different, where you need that last bit of performance that we saw some examples for, but that's not the base case. So does clean code imply horrible performance? Well, sometimes it does. Sometimes it does, but only if the requirements are extreme. In most cases, it won't matter, even in the world of C++. And your performance issues will probably come from something else. You won't have performance issues simply because you wrote clean or maintainable code. You will have performance issues because probably you mismanage your resources, or you don't make external requests the way you should. So I think you should perform low-level optimization only at a few places, only on the hot path, only when you measure and you can prove that you need. Otherwise, a bit worse performance and better maintainability will have a better return on investment for your business, for an employer where you work. Thank you so much. Any questions? I think we have a few minutes. Nobody? Then thank you very much. Thanks again. Enjoy the rest of the day.